Good afternoon. All right, welcome everyone to the kickoff for the 2019 Allen School Colloquium. I can now officially say this is the second annual Allen School Colloquium, and I hope you are all as excited as I am. I do need to do one thing really quickly. Hold on one second. Okay. So I'm not teaching this quarter, but my mom always wants to see my class, and so I figured I'd show her all of you, which will be like the best looking photo I've sent her so far since I've been at UW. So for those of you who are new to the department, the Allen School Colloquium is an event we have each year where you give the talks. It's a great way to see what different groups are up to and hear about your fellow students' research. So today we have a wonderful lineup of Sammy, Max, Aditya, and Robbie. And Sammy's going to kick it off telling us about trace reconstruction. So I'll hand it off to her.
Thank you, Zach. I have to wait for this thing to connect again. There we go. Okay. So yeah, I am Sammy, and we called this like the Hodgepodge Colloquium, which is partially true. But really, this is the softball team colloquium. So this is all people who are on the softball team and either love being on it, like Max and Robbie, or hate being on it, like me, and would like more of you to play so that I don't have to show up to as many of the games, or Aditya, who is like new and excited to join softball. So you should join the Slack channel. Also, theory's boring, so just join the Slack channel right now. You don't even have to listen to trace reconstruction. It's all good. Okay, so what is trace reconstruction? So trace reconstruction is this problem originally from the computational biology community. I'll talk a little bit more about that in a second. But as theory does, we have stolen the problem from fields and like completely changed it into a problem that we think is interesting, and now no one else really likes it anymore. So the original or the way that the theory community looks at it is the following. There is a binary string x of length n. And then we assume that you're given what we call some traces of this unknown string. So your goal is to try to figure out what the string is. So these traces that you get are basically sampled substrings, where you can imagine that each bit is deleted with some fixed probability. Just imagine like probability 1/2, the bit is deleted, so you get to see these little sampled substrings. So for instance, the last substring is what you would see if those gray bits had been deleted. And again, the goal is to learn the labels of x with high probability using the minimum number of traces. You can assume that you know the length of this string and that you know the deletion probability. So as I said, we stole this problem from the computational biology community. In particular, this is actually a problem that comes up for the missile group, and you can ask them exactly how it arises because I don't know, and I didn't go to my college bio classes, but a lot of them did. The important thing to know is that the full problem actually involves not only deletions, as I described it, but also insertions and substitutions. But in the theory community, we have studied substitutions extremely well, and it's really the insertions and deletions that we don't know how to handle very well. So hence, that's why I stated the problem with only deletions. So what do we know about this problem? We know that, remember that n is the length of the unknown string. We know that exponential and n to the 1/3 traces suffice to find the original string. This is using something called a mean-based algorithm, where you're basically just looking at like the expectation, like single bit statistics of the traces. As for lower bounds, we know that n to the 3/2 traces is required. And that's for like arbitrary worst case strings. If you assume that you sample the string randomly, then we know that exponential in log n to the 1/3 traces suffice. So the important thing to really get out of that is that we know that the trace complexity is somewhere between n to the 3/2 and exponential and n to the 1/3. But the big question, which we've all been thinking about who care about this problem, are can we reconstruct any binary string with high probability using sub-exponential traces? Okay, so like 2 to some polylog n traces. And the sad thing is that really nobody knows. People have been stuck on this for a few years, which in the theory community, being stuck for a few years is really not a long time. But it seems like the kind of thing where we think people are going to be stuck on this for a very long time, unfortunately. So what have people been doing who are interested in this problem when I just told you that people are really stuck on it? So instead, people have been really exploring variants around the space of trace reconstruction with the hope that it gives intuition as to how you could maybe make progress on that worst case problem that I talked about, or just exploring other interesting areas in the space. So for instance, I described the problem as saying that each bit has to be deleted with the same probability. Maybe you relax that or change it somehow. You can also imagine that instead of randomly sampling your string or it just being like any string or any binary string, you could imagine that you create like some alphabet, which you know you sample from instead. You can characterize the trace complexity in terms of the number of ones in your original string. There's also other earlier work on this more like biology related question about like reconstructing labeled trees when you are only given access to leaves of the tree. And so our work kind of fits into this realm of how do we explore the space of trace reconstruction in a way which may be meaningful to the theory community. So we've been looking at this problem that we call tree trace reconstruction. So my goal is to sell you on the problem, not really my work. So I'll briefly talk about some of our work here, but I hope I've just convinced you that trace reconstruction is kind of interesting. So tree trace reconstruction is the following. You assume that you have an unknown labeled tree X on n nodes. You can assume that you know the structure of X, say like you know that it's like a binary tree or something like that. You know the number of nodes that it's on, you know the deletion probability, and you know the deletion model, meaning you know like when one node is deleted, how does it affect the rest of the tree. The goal is to learn the labels of X with high probability from some samples that you receive. So to define how you get a sample, we need to define some deletion models. In the deletion models that we consider, you're going to assume that each node is deleted independently with some fixed probability Q, just like in the string case. You can assume that the siblings, like siblings of a certain node, all have a left to right ordering, and that the root node's not deleted. Those are just kind of technicalities. So we introduced this problem because we really wanted to bring more combinatorial ideas back into reconstruction problems, whereas they had been like very much so based in complex analysis. So just kind of like expanding upon the techniques that we can use. And practically, there's been some recent work in the like DNA nanotechnology world, which has led us to believe that, hey, maybe actually practically traces of trees are interesting to look at as well. So the deletion model that we define, called the TED deletion model, the tree edit distance model, is the following. When you delete a node, so like when you delete that gray node up there, the children of it move up in the tree. So for instance, when that gray node is deleted, its children have moved up to take its place in the tree. And this is inspired by computational biology settings again. And then I'll just state our results for complete k-ary trees. And kind of the big takeaway here is this stuff in red. The point is that when you have a k-ary tree, for k being the degree, you can actually reconstruct in polynomially many traces. And then you can do the same thing again using a different technique when the degree is actually much larger. So the point is that with this addition of structure, we are actually able to break that exponential barrier that I had mentioned for the string trace reconstruction case. Whoops. Okay, so open problems. Like I said, string trace reconstruction is very open. People really don't know how to improve, particularly that upper bound for the problem. And then there's lots of other variants that we are interested in. One that I like is instead of reconstructing the original string exactly, can you recover a string which is close in Hamming distance? And maybe you can do that with fewer traces. And this is like another example of a problem in this space, which is well motivated technically, but also practically. Okay, so thank you. And again, join the softball team.
Okay, and I think we're going to do a couple of questions really quickly in between. So,
what's up, Siva?
Yeah, so like, I'm confused about the model. Like, don't you actually, like, if the tree was just a path, don't you just get back?
Exactly, yeah. So it's like a generalization of the string trace reconstruction problem where a string is just a path.
But you seem to be getting results that are better than what?
Oh, sorry. So that's only for complete k-ary trees. I meant to state that for. Yeah.
Well, pardon the naivete, perhaps, of the question. How bad is this exponential like complexity in practice? Like in the area of DNA sequencing, like do you actually have exponentially many?
No, I believe you actually have like constant. A missile person could correct me on that, but like yeah, you actually want like constant, very very small. So exponential is like bad. Yeah. Okay. Thanks.
All right. I'm Max, and so unfortunately I can't answer any of those missile questions because I'm the stupid missile member. But so I'm going to be talking about fluidics plus computation, and because I've got 30 slides to do in 10 minutes, we're just going to skip most of the computation part. So I'm going to start by just telling you what fluidics is, because like a year and a half ago, I didn't really know what fluidics was either. So I'm really talking about microfluidics, which is the practice of manipulating small fluids. So here's a bunch of different technologies that you might want to do that. You basically have a little series of tubes on the left, and that's nice. It's cheap. It's single purpose, so that has some uses. And then in the middle, you've got a pipetting robot, which is basically a robotic grad student. It like picks up pipettes and squirts them into little tubes, just like a grad student would. And then on the right, you have a newer technology called digital microfluidic device, which I'll explain a little bit more about in a second. This is a video of one we've built here at UW called Purple Drop. And I like to think about this progression of fluidics as kind of the same thing that we saw in electronics. On the left, you've got simple single-purpose devices, which we still use because they're cheap when you want to like mass-produce something at volume that does a fixed function. But of course, people want general-purpose programmable things. And then, in electronics, we eventually got that, but they were expensive and big. And then, of course, now it's cheap and ubiquitous. And so I think that's the way we're moving in fluidics. And so that's why I'm excited about this digital microfluidic device. So how does it work? So that was the top view. Here's a side view. So we're like slicing through it here. You have a grid of electrodes. So you're only seeing through the plane here. And you've got a droplet squished between two hydrophobic layers. And then that white electrode is on. And if you turn the other one on, it moves. It's as simple as that. And you can basically, that's the key primitive. And if you put that together, you can move things around. You can mix and split them in parallel. And you can move them around to other peripherals you might have on the board. So in this video here, the little legs on the bottom, the little squares that they're not really moving to, those would be heaters. And you can move, you could attach any peripherals you might want onto the board. But so the question I want to talk about is, how do you program this thing? Right, because there's a lot going on. You might make sure you don't want your droplets to bump into each other, and you have to manage like where they are. So how might you program this thing? So you certainly don't want to talk about where the droplets are. You don't want to say like turn on electrode 1 at time step 1. That would be really bad. So what people currently do is they make these graphs. So they basically make a data flow graph that describes your protocol. This is a simple one. You input two things, mix them, and then output them. Right, and the edges connect kind of the data flow, the droplet flow in this case. And currently, the way things work is you take that and you run it through some big synthesis tool that uses place and route techniques from VLSI, because you're basically doing place and route. Like you need to figure out where would you mix this thing, how do you get the droplets there. Same thing with wires and modules on a chip. So then you get out a sequence of electrode actuations, and then you run that on the hardware, and it zips that droplet around. And then someone goes and collects the data. And that works well and good if you want to run one experiment. But a scientist probably wanted to run that experiment, so they designed that graph, and they're probably going to collect that data. And science isn't a one and done thing, so they probably want to run another experiment, right? And so this is where this kind of static workflow falls down, and this is where we want to put computation in the loop, right? So maybe the scientist is going to run a machine learning model to figure out what experiments to do next. Maybe it's just a simple if statement. Maybe they're sweeping over a parameter list. So instead of trying to come up with some new programming tool that can solve all of this with some fancy smanchy programming language, we're just going to use the ones we've already got, right? So instead of trying to create a fluidic programming language that tries to overthink what is a fluidic function and what does it mean for an if statement to execute on the fluidic device, we're just going to punt on all that and instead create a fluidic operating system that allows you to write a regular program in whatever your favorite programming language is. You can use all your machine learning models, your if statements, and all those wacky things, and you can run devices on a microfluidic chip. So let's see what that looks like. So at the top here, this is kind of our stack. These are all the cool things you might want to do with fluidics. These are all the awesome domains that I know nothing about that scientists are really good at. And at the bottom, you have this cool hardware that people might want to use to automate their experiments. So like our key idea here is put in a general purpose programming language instead of some special baked fluidic programming stack. And of course, to do this, we need to connect these, we need to fill this abstraction gap with a fluidic operating system. And what this is going to do for us is basically automate resource management. So just like, when you write to a file, the Linux kernel is like, okay, well, you don't really know how many disks you have. You don't know where they are. You don't know where the blocks are on that disk. That's okay. I'll find it for you. And I'll just give you back like, a file descriptor. So a simple number that represents like, okay, well, I actually know under the hood where that where those bits are sitting on disk. And it's gonna, maybe that disk gets corrupted, it'll move it somewhere else for you. So it's the same kind of thing, dynamic resource management for fluidics. So we call that stack puddle, and the hardware we've called purple drop. And one nice thing about this kind of abstraction is that you can write programs on an operating system and it can run on diverse sets of hardware. Maybe it runs something on a GPU, or maybe you have different kinds of disks or something. By having a dynamic abstraction, you can imagine kind of plugging and playing different types of hardware. So even if people want to use those pipetting robots, you could imagine using it with a system stack like this. And we have backends for the microfluidic chip, but we're working on the ones for the robots. Okay, so let's blow that stack up and break it down a little bit more. So the high-level programs that people write in Puddle today, you just write in Python. We have front ends in Python, Rust, and JavaScript, but we're just going to, I'll show you some snippets of the Python one because that's what scientists use. So yeah, you can write high-level programs. You can even write domain-specific libraries because you can share code because it's just Python codes. And it all hits Puddle through an API, right? So there's no compilation step. You're talking to basically the runtime system through a well-defined API. And then there's Puddle, the actual thing in the middle that's doing all the analysis and figuring out where the droplets should go. We're not really going to talk about that at all. I'm basically going to show you how you would use it and then some cool stuff we can do with it. And then there's the hardware, again, that I'm going to not really have time to talk about. Okay, so what kind of programs can you write with Puddle? So they're programs that look familiar to you because they're programs, right? So I promise this is the only code that I'll really walk through and make you read. So this code, has a user-defined function. And so all the things I'm going to highlight in green are actual innovations that, when we published this paper, this was the first time people have done in microfluidic land. So they don't sound, big to y'all because they are things that are very run-of-the-mill in programming. But these are things that, because if you look at microfluidics in the static way that people have been doing, couldn't really be done. So you can define your own functions and you can share code with people, and that's really nifty. You can also loop over unbounded data structures. So here we're defining a thermocycle function, which basically thermocycling means you repeatedly heat something up. So you take in the thing you're going to heat up, the droplet, and a list of the temperatures and times that you're going to heat it up to. So what do? Well, you loop over that list. Okay, so that's something that you couldn't do before. And then the underlined call to heat here is an API call. So this is actually dispatching into the Puddle runtime that routes the droplet to the heater and executes the heat. Another fancy thing you can do is run an if statement, right? So you can take a sensor reading, well here you're detecting the volume of the droplet, and get the data back and do something with it. So all in the same program. So you're computing over the data that you got back from the real world, all in the same program. So here we're taking a volume reading of the droplet. This is done with the camera. And we compare it to some threshold. And if it's too low, so maybe the droplet has evaporated a little bit, we pump in some more water with the input command, and that's an API call, and we just add it right to the droplet. All right, and because this is just regular vanilla Python code, it's compositional, right? So if I gave you the thermocycle code in a library, you could write PCR or polymerase chain reaction, which is something you might do to duplicate DNA. It's basically a simple instance of thermocycle. So you wouldn't have to write thermocycle on your own. You could use the method that I gave you. Okay, so that's really nice. You can write all this fancy code in Python, and it will run on the device. So like I said, all these go through API calls, which hit the Puddle runtime, which I am not going to talk about at all because I don't have enough time. And at the end of the day, Puddle, crunches on the commands that it gave you, and it eventually calls out to purple drop, which here's a nice big image of purple drop. That eventually runs your code. Cool. So again, just to tell you some of the cool things you can do with this, there's kind of 3 things you could do with Puddle, and they're all sorts of decisions that you couldn't make before. So you can make decisions at the execution level, which is where you take sensor data and you feed it back into the planning loop. So Puddle's using this to make your program run better. And one good example of this is droplet detection. So Purple Drop has a camera on top, and it's constantly looking at your droplets. It's using a very, very simple computer vision, and it's detecting how big your droplets are and where they might be. And what it's doing, it's comparing that with internally where it's expecting your droplets to be. And so if, as is common on this technology, a droplet fails to move as planned, we can catch that and reroute around it. And we can do that dynamically because we're not committed to a particular plan ahead of time. And that's the the annotated computer vision algorithm working in real time. So it works in real time, and this graph basically says it works. And if you don't have this error correction, it's hard to do much on the device because errors are common and you need to correct them.
Your time's up.
My time's up. Okay, that program that we showed you, that was the first time anyone could run PCR on this device, so that's pretty cool. And we wrote a key DNA store. It's like a key value store where you give it a key and you get back DNA. Okay, and that's it. You can watch the animations finish. I'm done.
Are there any questions for Max?
Sorry, I need this.
Really cool talk. What is the debugging experience like? If I make a mistake as I do when I write Python code, what's my experience in figuring out what went wrong and how to fix it?
So debugging like your protocol probably isn't going to be too much different from debugging your Python code, right? That's one nice thing is that you're just running Python 2. If you want to do print line debugging or even invoke the PDB and run your protocol interactively, you could totally do that. Debugging the hardware is a nightmare. It's like magic when it works, which means it's like magic when it doesn't. So it's very hard to figure out what's going wrong. Yeah.
So you set up this very nice analogy with conventional operating systems. I just want to write to a file. I don't even know how many disks I have. But the thing is, maybe once a decade, I go to write a file and says, sorry, there's no room on the disk. Imagine you have just constant resource exhaustion issues because it's like this big or whatever, right?
Yeah, so you can totally run into resource exhaustion. It's really kind of related to how many live droplets you have. So the scheduler, because you don't get to say when things run, the scheduler has a lot of freedom in sequencing things that you thought should run in parallel. But if you don't have enough resources, it'll run it. But yeah, you totally could come up with a case that does that. We are picturing a case where you instead of one of these devices, you have a gajillion of them all linked together. In which case, this starts to make more sense. I think there's one maybe over there. No. Okay.
Yeah, I'm a new grad student, so yeah, most of you didn't meet me. Can I have a quick show of hand? How many of you do the pixie dust name machine learning? Yeah, cool. So the pixie dust name machine learning? Yeah. So the fancy term. So essentially I'm trying to combine two of these hot topics like machine learning for Internet of Things. So my research, which I did at Microsoft Research India, was to enable this machine learning, complex machine learning algorithms in 2 kilobytes of RAM for the Internet of Things. I'll be talking about one particular algorithm which enables deep learning for 2 kilobytes of RAM for time series of data. So I call this the edge of machine learning, but yeah, people thought it was for Microsoft Edge because I was in Microsoft, but it is not. So let me be very clear about the devices I'm talking about. There are these ARM Cortex M0 class devices which have 2 kilobytes of RAM and maybe 48 megahertz clock. They're maybe the weakest of the devices out there, and you can't even run a proper for loop for long enough without running out the battery. So that's essentially the scale we are tackling. And the flash is not great as well. We have 32 kilobytes, so that essentially means our working memory of anything should be less than 2 kilobytes, and our model can't be more than 32 kilobytes. So what's the impact? Most of these things are futuristic, but one of them actually the smart agriculture for disconnected farms, that's something called FarmBits, which happens across the lake in Microsoft Research Redmond. That has been pretty successful, but rest of the things are still futuristic. So let's hope they come to fruition. So just to be clear, so the models will be trained on the cloud like infinite resources. We don't care about how many GPUs, how many icebergs we melt, but yeah. Finally, we want them to be deployed on the tiny IoT devices which have very, very small resources. So shameless plugging of advertisement. So we developed a library in Microsoft Research India which has 4 cool algorithms, 2 in ICML 2017, 2 in NeurIPS 2018. We have 2 more coming up, one in BuildSys 2019 and NeurIPS 2019. So essentially it has 6 algorithms. Bonsai is a classical tree-based algorithm which fits in 2 kilobytes for classical machine learning tasks. Essentially you can replace any classifier which you have been using in your code bases and replace it with Bonsai or Proton. Proton is a KNN-based classifier. Whereas coming to the much more cooler thing, that's the deep learning. So EMI-RNN is a signal localizing tool for your time series data. And the thing which I'll be talking today is FastGRNN. It's a it expands to fast, accurate, stable, and tiny gated recurrent neural network. So it's a recurrent neural network which we expect it to be like 45 times faster than LSTMs and GRUs while maintaining the same accuracy. So why time series? Like IoT essentially gets the streaming time series data every single day. So we just wanted to see how we can leverage time series data and make some sort of insights out of it using machine learning. So this has been a joint collaboration with my advisors at MSR and a couple of people from Berkeley. So just a refresher for people who don't know what recurrent neural networks are, like they have been out there for like from 1989 probably, and they essentially are a intelligent way of recursive matrix multiplications which keep on accumulating some memory into the future so that you can leverage the entire distilled memory for some classification task. So all I want to show here is the most important term is the U matrix multiplying with the hidden state over and over. So if there is a long time series which keeps on accumulating memory, this U essentially U essentially becomes something like U to the power of T, where T is the total number of time steps, and this comes into the gradient step during the optimization, which leads to something called exploding and vanishing gradient. So you either have your neural networks exploding in gradients, they don't work, or you don't have your gradient moving in any direction, so they're just saturated. So you don't learn anything at the end of the day because of this problem, and this has been a known problem from like 1990s, and people have been trying to solve it. So one of the techniques which people came up with is called unitary RNNs. Because the eigenvalues of the U to the power of T term explode, what they did is they just constrained U to be a unitary matrix. So eigenvalues of the highest eigenvalue and the lowest eigenvalue are always set to 1. So you always project the matrix back into unitary space. So there is no chance your optimization is going to go bad. But the problem is because you are constraining the expressivity of model, your accuracy gets a big hit, and you require much bulkier models to work on this. So essentially, this stops us from deploying them onto the edge. Then comes the standard state of the art, LSTMs, GRUs, which have been there from 1994. They get the state of the art everywhere, but they are too bulky because they are too complex, and like most of these processes are single threaded. So we can't even leverage parallel processing. So everything is pretty expensive if we want to go for this. So we come up with something called FastRNN. So FastRNN is the predecessor of FastGRNN. FastRNN is one of the primitive RNNs which you can see out there. It's essentially a weighted residual connection that implies you are adding the current memory multiplied with a weight to the previous memory with another weight, and both of these weights are coupled essentially, and you train them with standard SGD, and you hope everything works. And surprisingly, everything works. But the only problem is we are still like 1 to 2% short of LSTMs and GRUs. So we thought like, what can we do? Because our inference time is as good as RNNs. So there's no overhead over RNNs. So we thought like, what can we do better? And there are some theoretical results. If someone wants to talk, we can talk later. But essentially, we for the first time proved that there can be a non-time dependent bounds for generalization and convergence in RNNs, and this is an upper bound comparison, so it's not fair, but still it's a first of its own result. So then we thought, why can't we match the LSTMs and GRUs, and we came up with a slightly intuitive and intelligent way of leveraging gating, which has been there in LSTMs and GRUs for a long time. So we reuse most of the information which RNN is using, and we essentially do some sort of affine transformations, very, very simple intelligent transformations, which essentially are multiplying it with a scalar and adding it with a scalar for just a subtraction from 1, assuming the entire information is bounded by 1. And we don't know why, but this works as well as LSTMs and GRUs. And this is like 4 times faster than LSTMs and GRUs. So we thought, why not push it further? So we took the matrices and made them low rank, sparse, and byte quantized. So at the end of the day, we are like 45 times faster than LSTM while maintaining the accuracy. So wherever you see your LSTM or GRU, you're finding it hard for the deployment, just replace that with FastGRN, and hopefully you'll get within 1% of the accuracy. Otherwise, just hit me up. So I was surprised initially because when we were designing this algorithm, we thought this would be only for the IoT task, but it generalizes pretty well. So the first 3 datasets are actually speech recognition datasets where we have short utterances of words like hello, Marvin, 1, 2, 3, and so on. And WakeWord 2 is a dataset which is actually a Microsoft proprietary Hey Cortana dataset. So we wanted to do Hey Cortana detection on device because, yeah, privacy reasons. I think just after we released the paper, Apple moved its WakeWord detection to on-device. So before that, nothing was actually happening on on-device. Everything was being streamed to your cloud. So every single word you utter even before Hey Siri is actually in the cloud. So we don't want that to happen. And you can use this to happen. And we generalized it to NLP tasks like sentiment analysis, language modeling. And then we also ran experiments on activity recognition. So essentially, so the left 3 bars are ours. So we are really good. Otherwise, the paper wouldn't have been accepted. So yeah. But the model size is something which I'm very happy about because this is log scale and like we are like super small. This is comparison with unitary RNNs. Like unitary RNNs, like we even get to about 200 times better model sizes while beating it handsomely by up to 2%. This is the crown jewel of the entire paper. We actually did Hey Cortana detection on 1 kilobyte of RAM, and we deployed it. And so the only caveat here is we assume that we get the featureized version of your spectrogram in because we can't afford to do FFT on the device. So if you get the featureized Hey Cortana in, we can always make the decisions using a 1 kilobyte model. We ran a bunch of experiments on real-world IoT devices, and we see it's up to 2 orders of magnitude faster than most of the other algorithms like LSTMs and unitary RNNs. So yeah, if you want to deploy an RNN-based model for IoT, I think FastGRNN is the way to go. So yeah, like it's just a new update. So we have about 700 stars. So please, I get more 60 more stars, and it improves my GitHub profile. So yeah. So we don't support TensorFlow 2.0, but yeah, we support PyTorch, C++, and TensorFlow. We even have CUDA optimized RNN cells for PyTorch, so give it a shot. Thank you. Yeah.
So that sort of like that accuracy, like 1% accuracy. I mean, right now I understand that's sort of just a numerical measurement, but is there future work planned to actually pin down why that happens and how far it generalizes? Like, is that something you're planning on doing in the future?
Not exactly, but we try to deploy this in like huge products in Microsoft, and this 1% is something which I observed there. Like in IoT regime, I still match the performance of LSTM and GRU, but it has some expressivity issues when it goes to like large scale data sets.
Okay, so you're saying that there's not sort of a general equivalence between these two things.
Yeah, because
we don't really have a good sense of when the everything.
Yeah, it's just experimental. So as long as LSTM works, I can guarantee you up to 1% error. But yeah, that's that. I can't always guarantee you matching LSTM performance.
Okay. Okay. Fair enough. All right. It's cool.
Sure.
The experimental results are still very good results.
Sure. Thanks.
What's the code size for the library? Because you said you did Hey Cortana at 1 KB, so you did it like the general library size. How big is it?
So the code is pretty small. Like the inference codes are written in native C. So inference codes are just like a couple of 20 to 30 lines of code. And once you write the serialization, you can do that. And we also have a compiler which was published in PLDI, which can take in all of our models and do the inference for you. Yeah.
You said that the unitary RNN is inherently stable, but then it's really bulky.
Yeah.
So is there, like, what's the trade-off for the fast RNN? Is there a similar trade-off?
No, so fast RNN is only limited by its expressivity because even though universal approximation theorem says all the RNNs are all powerful, but you are using a convex optimization routine to solve a non-convex problem, so we don't know when we hit the sweet spot. So, but empirically, when we actually do the experiments, like unitary RNNs are about 4 to 5% lower than fast RNN, but fast RNN is still like 1 to 2% less than gated RNNs and fast GRNN. So this is all empirical, but theoretically fast RNN's training is always stable, so you will never have the exploding and vanishing gradient problem.
These are great questions. I think we're going to thank Aditya again and have Robbie. And remember, these are your colleagues. So if you have more questions, find them in the research comments.
Can I have a quick note just for if you're using the mic, make sure you're holding it close enough to your mouth that it actually picks up.
Everybody hear that? You want to be heard. Just a second, guys.
All right, so this is joint work that I did with 3 undergrads here at UW, Nick, Ginal, and Sierra. The title for the draft that we have of this paper right now is a strategy-proof alternative to round-robin sub-tournaments. But for this talk, I've added a subtitle, which is, Are People Good at Their Jobs? And that's actually the question I'm going to be asking you multiple times throughout this talk. So I'm going to start by asking you about some Olympic athletes and asking you, are they good at their jobs? All right, so I'm going to bring up a video. This is from the 2012 Olympic badminton tournament. And you can tell it's 2012 because this video is in 360p. So I will be giving play-by-play because you can't actually entirely see what's going on. All right, so we're going to watch the team in gold. And specifically, we're going to watch this person in the back here. She's going to take a big swing and send the birdie directly into the net. Sending things directly into the net is going to be a bit of a theme. Here's a serve. It's going to go directly into the net. Another serve directly into the net. And a little later, a third one directly into the net. At this point, this gentleman is going to come here. He's one of the organizers of the tournament. He's going to give the teams a little bit of a pep talk and suggest maybe they try hitting the birdie into the net a little bit less often. The gold team really takes this to heart, and instead of hitting the birdie into the net, they just let it drop onto the ground. And lest you think this is just the purple team or just the yellow team involved, a little bit later, the purple team is going to serve, and they are going to miss by about that much. All right, so these are Olympic athletes playing their Olympic sport, and I'm going to ask you the question, are these Olympians good at their jobs? You do have to vote. Who votes yes, these Olympians are good at their jobs? Who votes no? All right, it's about 50-50. So watching just that 20-second video, you would probably say that they're not playing very well. In fact, you might even say it looks like they're trying to lose. And it doesn't just look like they're trying to lose, they are trying to lose. And in fact, that's why I'm going to argue that they're good at their jobs. So what is the job of an Olympian? Well, it's to win the gold medal. And the way this tournament was set up, those teams actually improved their chances of winning the gold medal by losing the match. All right, so how could that happen? I'm going to break down very briefly how this tournament works. So there are 16 teams. They're going to be divided into groups of 4, and you will play each of the other teams in your group. So that's 3 matches. After those 3 matches, the top 2 teams in every group are going to move on. The bottom 2 are going to be eliminated. All right, so the second phase of the tournament, for those top 2 teams, depending on which group you're in and whether you finished first or second, you're going to be put into this bracket over here. And in this bracket, this is just a single elimination tournament. These top 2 teams play, the next 2 play, the next 2 play, and the next 2 play. Losers are eliminated, winners move on. These 2 winners play each other, those 2 play each other, and then the last game, the 2 remaining teams play, and the winner gets the gold medal. All right, so the 2 teams we were watching are teams W and X in Group A. They know whether they win or lose, they're going to move on to the next round. It's just a question of, are they going to be A1 or A2? And because of some other results in the tournament, it turned out that D2, the second place team in Group D, was one of the best teams, the team that they were most worried about. And so W and X looked at this bracket, they looked at where D2 is going to end up, and they said, well, I don't want to play D2 for as long as possible, and given a choice of A2 way down here, or A1 a little bit closer to D2, I want to be further away. And so they said, I would rather be A2, and to do that, I want to lose the match. All right, so losing their match, not winning it, gave them the best chance of winning the gold medal. Or at least it was supposed to. Remember that guy giving them a pep talk? That was a little bit less of a pep talk and more of a threat talk. They were disqualified immediately after the match for not using their best efforts and for conducting themselves in a manner which was clearly abusive and detrimental to the sport. All right, so you could tell from the quality of that video that it was from quite a while ago. It was from 2012, and the Olympics happen every 4 years, right? So there was another Olympics in 2016, and after the international news coverage of these badminton players looking silly trying to lose a match, the badminton organizers had to do something, right? So they had to do something to change the tournament to make this not happen again. So what did they do? They kept the same basic structure, but they sprinkled in a little randomness between the two phases. So instead of knowing exactly where you're going to end up in the bracket, they changed it a little bit so there's a little bit of randomness in where you end up. It's not uniformly random where you end up, but it's not completely determined anymore. And what they said when they announced this change is that they had eliminated any player's thoughts about actively trying to lose a match or matches, irrespective of other match results, and that they had ensured such a regrettable spectacle would never be witnessed in badminton again. And the 2016 tournament happened. There were no incidents. So did the Badminton World Federation, when they redesigned this tournament, do a good job, right? Who thinks yes, they did a good job? Who thinks no? Again, split. My vote is going to be no. It's not too hard to construct another example where your teams are still going to want to lose. Right? I say it's not too hard. Here's what you do. You start with the scenario that happened in 2012 where the teams wanted to lose, and then you actually have it. Without changing anything about the scenario, the teams are still incentivized to lose. Now, you do have to think about it a little bit, and you do have to do a probability calculation, but they're still incentivized to lose. All right, so some of you are saying, wait a minute, Robbie, we're like 7 minutes into your talk, and all you've talked about is sports. Is this just a talk about sports? And no, it's not just a talk about sports. There is some computer science here, and let me get to it. Specifically, this is going to be a problem in algorithmic game theory. All right, so what is algorithmic game theory, or what's the problem here in algorithmic game theory? The tournament organizers did not properly align their incentives. The designers of the tournament wanted a tournament that was exciting for the fans, where every team was trying their best to win every match, and every match was very exciting. The players wanted to win the gold medal. Right, so what we have here is a misalignment of incentives. So mechanism design is a subfield in algorithmic game theory, where you design algorithms assuming that the inputs are coming from people who have incentives, right? And what we want to do is design a tournament here, an algorithm, a tournament where the incentives of the competitors and the incentives of the designers are aligned. Essentially, where wanting to win the gold medal inherently makes you, from the tournament design, want to win all of your matches. All right, so that's what we're going to try to do in the last couple minutes of this talk. All right, so we want a tournament that aligns incentives. All right, so it's not too hard to come up with such a tournament. What you do is you just have a single elimination tournament for the whole thing. All right, so take that second phase that they had and just make that phase the whole tournament. And you're never going to want to lose a match in this tournament, because if you lose, you have no chance of winning the gold medal because you've been eliminated. That does work, but it's not a very exciting answer, and it's not a very useful answer. In fact, this was the way the badminton tournament worked until 2008. And in 2012, what the badminton organizers decided is that they didn't want that anymore. Right? And why didn't they want that? What they want, I believe, is to ensure every team plays more than one match. Right? This is the Olympics. They have teams flying in from all over the world. These teams are going to come, and if they play in a single elimination tournament, half of them will play one match, they will lose, and then they will have to go home. That's very important. That's very disappointing for all the teams that flew across the entire world to play in this tournament. It's disappointing for the fans who get to watch them once, be disappointed that they lose, and then have to go home. All right, so these are the two goals we want: to align incentives and ensure every team is going to play more than one game. Right, so your first thought might be, well, let's just keep the group play and maybe add a little bit more randomness to that second phase. Unfortunately, that doesn't work. This is a result by Polly from 2014. Under some pretty reasonable assumptions, you can't have this group play as the first phase and do anything in the second phase that will properly align the incentives. Right, so if we're going to design this tournament, we can't be messing with the second phase. We have to actually change that first phase, that group play phase. All right, so this is what we're going to do. Right, so my conjecture when we started this project about 9 months ago is that what you should do is you should replace the group play with a double elimination tournament. Right, so what's a double elimination tournament? It starts out a lot like a single elimination tournament. On the top half, it looks almost exactly the same. But when you lose, you're not eliminated right away. When you lose, you go down here to what's called the loser's bracket. And you stay in the loser's bracket as long as you keep winning, right? So when you get your second loss, you are eliminated. Until you have 2 losses, you continue playing, right? And you just continue like that until there's exactly 1 team remaining with less than 2 losses, and then they can advance out of this group play, out of this first phase. Right, and my conjecture 9 months ago is that this works, that this properly aligns incentives. Now, one more time, I'm going to ask you, is someone good at their job? And of course, the job of a theoretical computer scientist is to make conjectures and then prove those conjectures to be correct, right? So do we think I'm good at my job? Who says yes? Who says no? You are far too optimistic. That conjecture is false. Luckily, my co-authors are very good at their jobs, and so together, we were able to come up with a different conjecture that is actually true. Right, so you can't use a double elimination tournament, but you can make just the tiniest modification, and then it will properly align incentives. Right, so what we do is as soon as we have 2 teams left, instead of those 2 teams playing until someone has 2 losses, they play just a single game. And whoever wins that game is who moves on. Right, so I'm going to actually prove to you right now that this works, that this properly aligns the incentives. Right, so in any game where you're going to be eliminated if you lose, you're not going to want to lose, right? So all of these matches that in green here, we've handled just with that statement. Right, then we just have to worry about the winner's bracket. In the semifinal game, if you lose, what you'll have to do is beat the other 2 teams who are remaining in the tournament, one right after the other. On the other hand, if you win, you just have to beat one of those 2 teams. So if you lose, you will have to play a superset of the opponents that you would play if you had won, right? So you're definitely going to choose to play fewer opponents, to need to beat fewer teams to win. And in the first round, we have essentially the same statement. If you lose, you're going to have to beat all 3 of the other teams in the tournament, one right after the other in elimination games. If you win, you only have to beat 2 of the 3 teams in the other remaining in the tournament in elimination games in order to win the tournament. Right, and that is the entire proof of the theorem. This theorem, one of the reasons that I'm so happy with it is it's simple enough to really fit onto a slide. And actually, if you take like maybe a little bit longer than I took here, I think you could explain it to Olympic athletes even if they don't have much math background. And really do convince them not to lose anymore in tournaments. All right, so that is our theorem. All right, so what are the takeaways from my talk? The first takeaway is watch the badminton tournament in 2012. It could get really interesting. Secondly, tell the Badminton World Federation about modified double elimination tournaments instead of group play, and help us ensure that such a regrettable spectacle is never witnessed in badminton again. Thank you. Dan?
So you didn't give us any intuition on why the traditional double elimination doesn't work?
Yeah, so why does traditional double elimination not work? So the problem is essentially, it's only in that first round. If you lose in the first, if there's a team that's better than you, that you don't have a very good chance against, you might be able to intentionally lose in the first round, face them in the loser's bracket, only need to get an upset once. As opposed to if you win, you might play them in the final round where you have to beat them twice. And even though it's 2 out of 3, you might prefer, if you're worse than them, to just have to beat them once down here rather than 2 times out of 3 naturally. Other questions? Christoph?
Actually, no, I don't have a question. Never mind.
Okay. Yeah.
You're telling us to watch badminton in 2020. Wouldn't this be evidence that the committee has done a great job designing the tournament?
I suppose under the there's no such thing as bad press standard, then yeah, this is quite possibly what they should keep around. Yeah.
Actually, no. I mean, it seems like from a meta perspective, the committee has aligned their incentives just fine by the method of if you try to pull the stunt, we will just kick you, you lose.
Yeah, this is a good point. So there's this external statement that they can make of, if you try to lose, we're going to kick you out, and therefore you can't try to lose. This was a particularly bad example of teams trying to lose, where it was very obvious. You should have to be worried, though, about teams trying to lose and being subtle enough about it that you don't catch them.
Fair.
Paul?
So there are other types of other sports, curling, and actually the softball, college World Series and things like that, where, so, you know, in College World Series you have multiple games to decide whether you want to win or lose. So like a single pairing isn't enough or things like that. Are there modifications that would allow you to generalize in some of these other scenarios?
Yeah, so are there things we could do to generalize? So this is actually one of the strange things about this statement. It holds for 4 teams. If you go up to 8 teams, we actually don't know how to make it so that teams don't want to lose. So this double elimination is actually, the proof is actually very fragile to having only 4 teams around. So as long as you keep everything in groups of 4, you might be able to modify it. I actually don't know ways to get bigger than 4, except by saying handle the size 4 and recurse. Brett?
One quick one, one longer one. The quick one is just to clarify, you're proposing the modified double elimination to replace the group play, and then you proceed from there to the standard knockout?
Yes, yeah, this replaces the group play. Then you can do either one. You can either go to the standard knockout, or you could do another version of this, whichever works.
The longer question is there a 30-second or so summary of the poly results about why group play inherently must lead to misaligned incentives?
Yeah, is there a 30-second version of the poly result? Unfortunately, no. His proof is a proof by exhaustion that had to be checked via computer, because he literally just said, here are about 5,000 cases. I wrote up in C++ a program that checks them all, and trust me, none of them work. Getting a short version of that proof is actually an interesting open statement. Lauren?
The one benefit to group play is you only have to play 3 games, which I'm thinking in terms of, like, I've been to so many Ultimate Frisbee tournaments that, like, time-wise, you have a weekend to do this. This actually, the double elimination winds up adding time.
So it looks like it adds time. It actually doesn't. So we're only having 1 team advance out of the 4 instead of 2. So we've actually gotten rid of one of the rounds in the knockout round. And there are actually only 4 rounds necessary here. Every team is going to play at most 4 matches.
True, but you have to play A, B, C, D, and then L1 and L2 actually happens after A, B, C, D happen, right? So it's not really balanced.
So A, B, C, D play all at once.
Yeah.
The losers and the winners play, so 3 and 4 happen. 5 happens by itself, and then 6 happens. And then remember, there is no 7. This is because we modified it to get rid of 7. So it's actually only 4 rounds, and it's taking the place of 4 rounds in the original tournament. Yeah. Should we? One more? Okay, Nathan?
So what if you know that you can't get gold? Does this still work?
If
you're trying to get silver, is it robust to lose?
Oh. That's very interesting. I don't know. But we have not put the paper on archive yet, so we can figure it out and type it up quickly. You can get an acknowledgement for asking that question.
Sorry, Chris, we'll take more questions offline. So thanks everybody for showing up. Please make sure to come back October 24th for the second installment of 2019's Allen School Colloquium. And until then, I hope everybody has a wonderful beginning of their quarter. Let's thank the speakers one last time.